but that's great.
Um,
I'm sure I would if I sat down with the physics.
anyways, so yeah, we sort of want to measure some obstruction. And so anytime you're studying like a cohomology theory, kind of in the back of your mind, try and figure out what is it we're trying to like, well, what's the obstruction we're trying to measure here? Or what sort of thing is like failing to hold. At least I have found that to be.
Well, at least in the case of like algebraic topology, so like, I don't know about homological algebra in general, but I know like from a topological perspective, it's a way of it's ways of characterizing topological spaces by the kinds of thing. At least for de Rham cohomology, it's like the kinds of forms that you can have on them, right?
Yeah.
And so, yeah.
Yeah, so yeah, that's kind of the other part. It studies obstructions and uses obstructions to classify. Okay, so now we kind of get to, I'll sort of follow the book. Basically now, we can take, so we have what's called a chain complex. I don't know if the book uses this term. I'm going to use it because this is what the term
They call it differential complex.
Okay. Chain complex, or yeah, a differential complex. Chain complex is, it's going to be a collection of, in our case, vector spaces. And just a drawing going up or down. Okay. So we're going to have our differential elements here. So basically, we have these maps. So this is, sometimes you'll see like, they'll put a little subscript there. And these satisfy the property that d composed d is equal to 0.
Yeah, so D here is I don't know, maybe this is, but it's an odd derivation, so it satisfies a Leibniz rule for at least for what we're doing
Yeah,
here,
yeah,
right?
for what we're doing
It
here.
satisfies a Leibniz rule property, and it's odd, so its commutator is an anti-commutator, which means that that property you could also write as 1/2 of the commutator equals 0.
Which is just d equals 0.
What?
Or it's funny that they put the 1/2 there.
Yeah. Oh, sure, because it's
Yeah. I guess
you could divide
unless
it
there
out.
were a field of characteristic 2.
Yeah.
Yeah.
Okay, but so it's nilpotent is sort of that property, and then also the other thing is it has this property, so its degree is either plus or minus 1. So the one you drew there was when it's plus 1.
Yeah.
So it either takes you up in your grading or it takes you down in your grading.
Yeah, and so in the case where it, let's see, we'll use a lowercase d for. And then, but we're still going to have the same property that d squared is 0, or yeah, this is sometimes abbreviated as d squared. Basically, as you study homological algebra, you'll realize that mathematicians get really lazy and don't like to write the subscripts, and so we just, yeah, usually it's just written like d.
Yeah,
Just
well,
have
if
to
you,
figure out.
I mean, I could imagine with the subscripts you could have a different sort of operator.
I guess,
But you,
yeah,
but the
that's
point
true
is
for-
that D is an operator that works on your whole. The way we have it here is D is an
Yeah.
operator that works on your whole graded algebra.
Yeah.
Right. It's
No, that's a good point, yeah, because you can define these, like it doesn't have to be, like
Yeah.
it just has to satisfy the property that any two consecutive compositions gives you 0. So basically, we call it homology if our D is like going down, and cohomology if it's going up. Really not that big
and
of a
that
difference.
corresponds with the degree of D being plus or minus
yeah.
1, right? Okay. And then
It's-
like
Yeah.
cohomology, I can think about that in terms of I can think about that in terms of like the exterior derivative, right? Because that goes up, and then homology you think of in terms of like the boundary
Yes,
or something
yeah,
like
the
that. So
boundary
something that
operator.
maps you to the boundary, or like if you have like a CW complex, right, where it's constructed
Yeah,
as this skeleton, that sort of
yep,
thing.
the
It
simplices, it
maps you
to,
down.
like the alternating sums.
Yeah,
or-
something.
yeah, yeah,
Right. Okay.
yeah. So yeah.
I don't really know that much about that, but I know a little bit. Okay.
Basically, yeah. It's
But
just a
this
way of-
abstract thing makes sense to me.
Okay.
Um,
Are you guys make sense? Make enough sense?
I understand, I don't know, I read a physics paper where they did this, they did stuff on a lattice, and they were using it like plaquettes and lines and things to define all of the, like,
Yeah.
a boundary and a co-boundary operator. and
Yeah, because what you can do.
then use this to define a quantum field theory on a lattice, and just had their co-boundary operator was what they treated as a derivative.
Oh.
Anyways, it was a way of, it was more complicated construction than they probably needed for what they were doing, but they were just trying to do it in a way that was,
Yeah. No, yeah.
that could regularize the
If you
theory.
look at like the definition of the boundary operator for like singular homology, it looks messy. But you're basically just, you're taking like, if you have like a simplex, it's like oriented like that, you're just turning it into like, you think of like formal linear combinations, so each of these is gonna turn into like something you're summing over. And then, it's a little bit of a weird.
For the lattice one, I could see, I mean, there it was nice because everything was like, it was like square, right?
Yeah.
And so there I could see how, like, when you did it the right way, the differential operator gave you some finite difference approximation, or like normalized, if you normalized it the right way, the differential operator would give you some finite difference approximation of a derivative.
Oh, interesting.
And I was like, oh, okay, I see how this maps onto derivatives. So it's like, there it was like a bunch of oriented, points, lines, plaquettes, and then whatever the cells, right?
Are we in a position yet, and if we're not, that's totally fine, but are we in a position yet to address some of the stuff that we've developed so far in the book? Or we still need to?
We can talk about it probably. So I think we wanna get a bit further, but.
Yeah.
But
Okay, so a little bit more of this, okay.
But he develops, so there's gonna be one operator with degree 1, and that's our longitudinal exterior derivative, which we've already talked about.
Sorry.
And then there's gonna be,
And longitudinal means gauge.
which means gauge, right? Yeah, it means it's
In the direction of the, orbits or something?
yeah.
Like it gives you a vector
So
field
there's-
that pushes you in the direction of the orbit.
Yeah, so there's these longitudinal vector fields, they push you in the direction of the gauge orbits. And then if you look at the exterior algebra of these longitudinal vector fields, and you look at the exterior derivative on that, that's gonna be one of the things we're gonna be using to construct our BRST symmetry. And then the other one is the restriction to it'll be a degree -1 operator, and it's sort of like, if you think about it like a boundary operator, except it's like sending you from something to your boundary, instead of now it's sending you from your whole phase space to the constraint surface. And that's what he calls anyways, but he
Okay.
defines, that's a example of a resolution, which he defines here.
Okay.
And that's one of the things I didn't quite
Because I think we need
understand.
some more of this, but I also think that as soon as we start talking about some things that I've already learned, that it might actually give me a
Yeah.
handle,
So-
a place to, put these ideas.
Right. Okay, so we take the kernel mod, the image, and that gives you the cohomology algebra.
So given a chain complex, the cohomology, which we use an upstairs n of defined to be
So one thing I can tell you here is that H0 of the longitudinal exterior derivative, so like the gauge exterior derivative, on the constraint surface is our gauge invariant functions.
Which could be things like measurables.
Yeah, things
Okay.
like measurables. Right, those are sort of their,
Yeah, so, yeah, the way we measure our obstructions is we take the kernel, so we know that the image is contained in the kernel, since if we just compose twice, we get 0. Yeah, another way of saying this is that the
yeah,
image of D is contained inside the kernel of D, and so we're asking, like, how well can we reverse it? And so we take these, these quotient spaces. Yeah, and then what we can do is we can define, like, we can turn these into an algebra. The book uses the notation H star. I usually use like a script H, just something like that. And this is defined to be the sum over n of our
yeah,
cohomologies. And we don't really like thinking about this in terms of homology.
yeah. Well, I mean, here they also define it for the homology.
which is really weird, because, like,
Yeah,
I guess, yeah, so I guess you also have,
I mean, I don't know.
there's some, like, algebraic reasons why we care a lot more about.
The cohomology is nice.
So
and
what it's
all.
related to is we have the diagonal map, that's gonna map V, to V times V, or, sorry, to the ordered pair.
Yeah, yeah.
Essentially
I
the reason-
I knew what you meant.
Yeah, the reason we care more, so then in cohomology, we can sort of look at, like, doing this over certain coefficients. So, like, instead of mapping to R, or like mapping to, like, Z or something, or hold up, let me think. Basically, it's related to the fact that when you're looking, like, you can view your cohomology. Do you know what a functor is?
Yeah.
Cohomology is going to
I
be sort
went
of.
to the first 2 weeks of the homological
Oh.
algebra class they taught here.
Basically, yeah, cohomology is going to define a conjugate functor, and so our diagonal map, we're going to have an induced map from. We're going to have an induced map going the opposite direction.
Right, and
And
covariant
so-
and conjugate in this section is like, in this sense, is like you in the
Conjugate
turn all
reverses.
the arrows. Yeah, you
Yes,
just
yeah.
have the arrows the other way.
Conjugate reverses the direction.
Right, which I have to think. Maybe I have to think about what that actually means, but yeah.
Yeah, it's a lot of times corresponds to pre or post composition.
Yeah.
Basically, though, this gives us sort of a natural map from V times V into V, which we can then use to define a product on here to turn it into an algebra. With the way homology works is it's a covariant functor, and so we're still going to have V to V times V, and so there's not like a natural way of sort of like
Sure.
taking something in V times V and turning it into something in V.
Okay.
But yeah, that's not
Okay,
related
can
to-
I ask about, so I know what a homotopy is in the topological sense. I don't understand how the definition they use in 8.23 would be a homotopy.
Yeah, so it's called a chain homotopy. So a chain homotopy is the algebraic version of like a homotopy. The
Yeah.
connection is if you take a homotopy in the topological sense and look at like the stuff you use to define singular homology, your homotopy equivalence turns into like a chain homotopy.
Okay.
It's a
Can you,
stupid.
is there anything that's easy to visualize with what's going on in 8.23?
Not that I.
Or should I just take 8.23 as a definition?
I would just take it as a definition. Yeah, we say that
Okay.
F and G are homotopy equivalent. If there exists a map sigma. Now let's see. D is gonna. I'm just gonna work over cohomology.
Yeah.
So degree plus 1. So let's see, this takes us up a degree, so this needs to take us down a degree. -1 such that F minus G equals sigma D. Yeah, I wish basically this is just gonna correspond to like they differ by a boundary.
Sure. And that corresponds to, okay, so let me just read through the definition they have here. So they have let capital lambda be a linear operator that can be diagonalized, i.e., okay, so that means it can be, can be written in this block.
Oh, it's basically we can define it on everything in our chain complex. That's what that's saying.
Yeah, but are we saying it maps everything in our chain complex back to something the same?
Yes.
Okay.
So yeah, that's like in the algebraic sense, you call that a chain map.
Okay, so it's block diagonal on the chain complex. Is that the idea?
I've never thought about it in terms of matrices.
Okay.
Sorry.
So are you saying, okay, I guess, are you saying it maps everything in Cn back into Cn? Is that what you're saying?
Sorry. Let me think about this. Okay, so we're gonna have. Sorry, just a second to think about this. So we have a map lambda. I guess is how we define it. So we have map lambda from. That's right, yeah. C to C prime. And since we're thinking of C as like a direct sum. Basically, the idea is we want a map where this diagram is gonna commute at every degree.
Okay.
Which I think the way it phrases it there, basically with it being diagonalizable, I think is gonna correspond to.
Yeah, that what you've written down that's the same thing as it being, but it's not necessarily your original grading. It might be some different grading. Is that what you're showing there? So we've got Cn to C prime. N plus 1. So what does the prime mean there?
Yeah. Oh, sorry. This is just another. Yeah. This is another chain.
Grading.
So, just another chain complex. So it could
another
just be this,
chain, maybe not a grading of the same chain complex.
Yeah.
Another.
Just an arbitrary one.
Okay.
I guess if it's the same one though, yeah, it could be a different. We could think about it as a different grading.
Right.
Right.
Well, and I think the one they have is they want it to be the same. One, but okay, fine. Okay, I that's fine. Okay, so linear operator is coming from this D.
And then we have
yields.
D and D prime, and basically.
So when the anti-commutator leads to gives us just some new way, some weighted new way of grading it. Okay. Okay, but if there exists a contracting homotopy, that means the cohomology is trivial for all K. Okay.
Let's see. That's gonna
And
mean
trivial has to do with the modding out part, or?
Yeah, it means that when you mod out, you just get the zero vector left, or the zero vector space.
Yeah.
So it means the kernel is the image, right? It means you're modding out by everything.
Okay,
Yeah, because then if we think about
there's nothing else, okay.
kernel D.
But that's fine. Okay, I mean, okay, so I guess for the reason this is useful, I guess, this is my question. So the reason this is useful in 8.2.7, so this idea is just, this is a way of proving that the homology, the kth homology class is trivial or something.
Yeah,
Okay.
basically. Yeah.
So in algebraic topology, I think that would be something like there's no holes or something like that, or at least for the first one.
Okay.
Yeah. But yeah, so it's the reason it's called homotopy is it is related to like.
Yeah, I'm sure if you,
There's
a correspondence in the right, homology,
Yeah.
homology or whatever.
And a contractible space is one where the identity map is contractible, or has that property.
Right.
Yeah, basically, it just tells us there's no obstructions, all our homology is gonna be trivial, except for like our zeroth homology, but we don't really care that much about.
Yeah, okay, so,
Okay.
okay,
Any other questions with that?
yeah, so that, I'm just gonna think of this as one way of checking that it might have something to do with homotopy in the topological sense, but I don't quite understand the correspondence yet, but maybe we'll just think about this as some way of checking whether cohomology, I guess, class is trivial, or
Yeah.
like it, yeah, okay.
Okay.
Which means, like, in the ideas you were talking about, it means there's no obstructions, right?
Yeah.
Okay, so the differential D also defines a cohomology for the Lie algebra of derivations. Okay, a derivation is D invariant or D closed if it commutes with D in the graded sense. Okay, so we have a D. Okay, so maybe here, I'll just write this up and we can look at what can I erase this, right? That's just the definition of ideal. Which is, yeah, because like here, this is getting to the things I just sort of want to understand. Because up until this point, maybe I don't understand it at a super deep level, but it was like, reading through it, I was like, okay, I get this. Okay, so the differential D also defines a cohomology for the Lie algebra of derivations. So we say, so delta is just some derivation with the Lie algebra just being the commutator. Okay, the set of D closed okay, so we say that delta D equals 0. So I think this is definitional. Delta is D closed. So normally when we say, okay, a closed thing is something
It's in the kernel.
that's in the kernel, right?
See why? Oh, okay. I think what they're saying.
So I think this would be like, okay, so if we're thinking about these as, so these satisfy Leibniz rule, I'm just gonna say we've got something that backs on. I'm not gonna think about parity, maybe for right now I'll just assume everything's commutative. Then this is gonna be delta,
And it is a derivation just broadly things that satisfy,
yeah.
that acts kind of like differentiation with the, so it's got a Leibniz rule.
Should that be a minus?
Yes.
Okay.
Minus, and then maybe with some epsilon, but this is a very abstract thing, I'm just saying, for whatever the
Yeah.
sign of this needs to be.
Okay, the way I would go about thinking about this. Okay.
So because, okay, the thing is, okay, so we have a derivation, he didn't talk at all about whether it was, what the parity was, did he? He says that D generally, though D is an odd derivation.
Yes.
So this is something I normally think of as a,
degree 0.
So D is?
D is odd.
Yeah, so I think it's, since we generally think about like this acting on like a space of functions, that's gonna be degree 0, and so if you think about a graded Lie algebra, it's gonna be a negative, it's gonna be a minus there. If F was something like a,
That was, So you're saying if delta's degree 0,
Or, sorry, if f is degree 0.
if f is
Yeah.
So
yeah.
closed has something to do with the kernel, right? And you're trying to, is that what you said,
I
or
don't
no?
like that he's using declosed. To me, this
Oh,
is more
that gives you the wrong impression?
Yeah, because declosed would mean that, like, or in my head, when I think declosed, I think d of
Well-
delta is always 0.
No, but I think this is just, it's the way that D is acting on delta is by the because it's the same definition that he uses for closed and exact, is he says that
Oh, I see what you're saying.
delta equals delta bar D. So it's just the way that D is acting on this differential.
Oh, right.
operator
That's
is-
right. Yeah, because we're defining a new chain complex here where each of our things is
Yeah.
going to be endomorphisms, or sorry, derivations.
Derivation. So we're
Yeah,
sort of
okay, yeah.
defining.
And then our
Right.
differential becomes.
So the idea is we're doing this sort of thing.
What's the bar?
Some other differential. Some differential.
So what is this,
So-
is there like an exist statement there, or
This is
what?
this is what we mean. This is a definition. So this is.
I know, but like,
Yes.
for,
Yeah.
there
if
exists a
exists, yeah.
delta bar or something?
Yes.
There exists some delta bar such that this is true.
Okay. Then delta is said to be exact with respect to D.
Because essentially what we're doing here is we're defining a new, so we're taking like, let's say, just say it's derivations on like a graded algebra A. We're essentially saying like n minus 1. So we're defining our chain complex or differential complex like this, where our differential now is going to be the map.
Commutator with the differential.
Yeah, with the differential on our original chain complex.
Right. Right. That's right. And now it's these are Lie algebras, so they have Lie bracket is defining what the
Yeah, because
rather than multiplication, it's a
our space of derivations is going to form a Lie algebra, and so yeah, we're
Okay.
Yeah.
going to find our differential.
So, but is the terminology closed? Well, I mean, so is there a,
It's
is the terminology like good terminology because of
yeah,
this?
it's
no,
good.
I
It's good
was
because
thinking
of
about
this.
it like a level 2, or I was thinking about it on the level of like
right on the
spaces,
level of the C
which
C ends of the
somewhat
A.
has a nice interpretation. I think it has to do with like a certain
Oh,
diagram.
really?
Well, because yeah, if we think about this being 0, that's going to have to do with like the diagram commute, like a diagram commuting. So I assume it's probably related to that. I don't think that's important to this, but
Yeah.
Yeah.
And well, we thought about this the other day, right? Okay. This is something we did the other day. So anything that satisfies a Leibniz rule is gonna satisfy. Okay, what was it? It was like we were thinking about geometric quantization when we were doing.
Which
it.
are
But-
erasing, yep.
But think about so if there's a natural correspondence from operators to functions just by multiplying, like it was okay, so it was like, so if we think about f as an operator on functions that's just multiplication by this function, right? Then anything
Oh.
that satisfies a Leibniz rule is gonna have the property that x commutator f is just x acting on f. I
Which
think.
means the vector field, say, which I could write with derivatives and stuff.
Right. Where this is
yeah,
Directional
x sub I
derivative.
del I. That.
Yeah, okay.
yeah, but the point is, yeah, that was specifically for, but we thought it seems like sort of if there's a way for this to act on this, and if there's a way for this to do this. Anyways, the idea is if you sort of, if you think of functions as, can you think about, I don't know if that's quite right though, but anyways, never mind. But the point is, this is just the way that we're saying our differential acts on the space of derivations,
Yeah.
right?
And it's not entirely misleading, the language.
No, again, I was thinking about it a level
Mhm.
two, yeah. We're saying closed exactness in terms of this sequence over here.
Yeah.
We define our differential to be the commutator with,
Right.
yeah.
So the set of D-closed derivations is a Lie subalgebra of the set of derivations. Okay, that seems reasonable,
Yeah.
right? So, and then this follows from Jacobi identity. I'm sure we could work that out. Okay, a derivation delta is D exact when it is the commutator of another derivation with D, which is that second thing there. D exact derivations are D closed. And is that because
I think that's gonna follow.
the zero is the
Or-
zero operator a derivation? Because you just set everything to zero,
Yes.
and so you just
Yeah.
right. Okay. Wait. So wait. Actually, wait. Is that what I'm thinking about? No. Okay. So I need to show.
Because we wanna show that this is going to be zero.
Right. Right. That exact. Right.
And let's see.
Oh, that's.
If we think about this.
Oh.
I think that's pretty.
Yeah,
sure.
because with the Jacobi
Yeah.
identity,
Yeah.
you're gonna get two D's together.
Yes,
You're
that's
gonna
right.
get two
Yep.
D's together, and D
Yeah.
is
Is a
importantly
derivation.
it's
Or-
nilpotent.
sorry,
I
that's-
think right is
It's
we
a,
need
yeah, it's a
that.
Yeah, okay.
differential. Yeah, it's nilpotent, so yeah, that's gonna be zero.
Okay.
Yeah. So
Yeah.
using Jacobi identity and
Yeah, I
properties of
actually,
D.
in presumably some kind of really lowbrow way, ran into things like that all the time, where I was using the Jacobi identity, but two of the things were the same,
Mhm.
Yeah.
and then things are kind of trivial. So,
Right. So I bet you use Jacobi identity because two of the things are the
That's gonna call
same.
one of the terms.
Yeah, one of them it's gonna be you get commutator of D with. Wait, but
one of them
commutator
is
of D
with,
with D is zero. By
because
the,
you do have a
That's the
composition of them.
nilpotent.
You do
yeah,
have a-
that's the nilpotent thing. So
Yeah.
okay, so it's gonna be the same. Okay, yeah.
Mhm.
Okay, yeah,
I guess, yeah, we wanna think about it in terms of the graded ones, and, yeah.
yeah, but I believe that.
Yeah, I
okay.
do as well.
They actually form an ideal. Okay, for the commutator Lie algebra D. Hence, one can define the quotient Lie algebra. Okay, so they also define H.
Oh, I guess that's what.
Star D. Yeah, I mean it's. So that's why he uses this H script H star D. For this is closed mod D closed
Yeah,
mod D exact.
and so, yeah,
But this is specifically for derivations.
yeah,
Right?
and so we're taking the the cohomology of this sequence here.
Right, so this is
Input.
just saying that this chain complex induces a chain complex on the set of
Yes. Yeah.
derivations. Okay.
Yeah, that's exactly what it's saying. And yeah, then you have the corresponding homologies as well.
Yeah. Okay, so
Getting close to gauges, kind of thing.
yeah. Yeah, so I think we've got a couple pretty thick, dense things to get through, and then I think, so like there's these 3 pages that are pretty dense stuff, and then he's like, geometric application, the BRST construction in brief. And so, okay, so we have a differential delta and an odd derivation. Okay, so so this is a differential, so that is something that generates a cohomology, right? It said
Yes.
differentials are,
Is there any kind of a hint? I mean, Weinberg mentioned some things, but you know, what the cohomology is going to be about from the point of view of
So,
the stuff we've been studying?
my understanding is that so the stuff we went over with Tuesday, with like the quotienting out, and then like, oh, but we want to quotient out this other thing. Essentially, what we're doing there, you can translate to sort of a manifold setting of, yeah, you're picking a representative. The idea, what we're trying to do here is we're trying to essentially turn all of that into just an algebraic thing, and then we want to say, let's study our sort of the like quotient and manifold by studying the original one. And the way we do that is you kind of have to do this weird like defining a differential, and then when you work through all the math, what ends up happening is you get that like the homologies that are defined off of these differentials gives us what we want, in the sense of it lets us study like our quotient space by studying the original space.
Yeah, so so I think that's probably right, but to talk about it more specifically to sort of what we're doing for gauge theory.
It's that business of doing stuff on the
Yeah.
on the surface. On the
Right. It's doing it on the surface, but we want to define it sort of on the whole space in a way that it sort of makes sense, and then we and so we enlarge our space, but then we give it a differential on that space that generates the same. So here, okay. So let me talk through this a little bit.
Yeah, big picture stuff.
So remember the longitudinal derivative, right?
Yeah.
This is going to be on our constraint surface. This is our observables, right? Our gauge invariant functions. So these are.
Mhm.
Right? It's you basically this is basically modding out by the flows of the this is just saying that we're modding out by the flows of these longitudinal gauge vector fields, right? And so that's why it's 0, well, because it's functions, right? Sort of modding out by all of the behavior. So the idea
for me,
is
it's
now,
like the potential fields underneath that sort of construct the observables. Like they have their motion, non-trivial, with the gauge, but the observables don't go anywhere.
Yeah, right. And so we need to mod out by those. It's like modding out by the gauge transformations, right? And so this is just a way of saying that. But then the idea is, okay, let me skip ahead to the next chapter just to make sure I'm not saying anything wrong. But okay, maybe we just talk through as much as we can of the next chapter. I think most of it we can talk about. So the idea is we construct another differential, which he calls S, and I think this is which is the generator of the it's the generator of.
I mean, it came up a long time ago when you first talked about BRST, like 18 months ago or whatever. But yeah, and I never knew exactly how to think about that, but yeah.
It's the generator of. It's the generator of what? It's the generator of the BRST transformations, right? And then we construct it in such a way that we still have.
So when I think of generators, I think of these things that I can kind of exponentiate to get to something that's kind of the macroscopic, not infinitesimal thing.
Yeah.
But I don't know if that has anything to do with this.
Generators in like an algebraic.
I always think of like generators, like one of the things I noticed about this whole, what do we call it, simplification of the dynamics, is that unlike for just thinking about the Euler-Lagrange equations without that in mind, you actually have these, first order differential operators, the exponentiation of which actually gives you the solution to any initial value problem. But can also do things like map your, you can have these limited ones that are just in the direction of the gauge. And you don't have to think of them as, t is in the exponent. You can just have some other parameter there, usually called epsilon, because I think of it as like a symmetry generating thing, a Lie group kind of generating thing.
Yeah,
Is it something that we?
it's like that.
It is a small thing, right? Oh yeah. So that tells me.
He creates he eventually creates some function omega such that this is true, right? So this is what S means, right?
Yeah, and I like to think of that S as something kind of small, right?
Right. And then we have so this generates gives us a canonical transformation, right? And so that's the sense in which this
And that's a Poisson. That's a Poisson bracket there.
This is a Poisson bracket, yeah.
Or it could be whatever if you had whatever kind of.
And the nilpotency of S is equivalent to this property for the Poisson bracket. But this is gonna be like a Grassmann number type. So this normally would be trivial,
like
but
S
this
is
is Grassmann valued.
Because
so
S is S nilpotent or something. Or no, it anti-commutes with your other guys or something like that.
Yeah, well, so it turns out that the right way to do this is that you have to introduce these ghost fields, right, which are Grassmann valued. They have odd parity, right? And so that means that this isn't just immediate, like okay, if this was just a regular C number function, this would be 0, right, immediately, right? But here, this ends up becoming like the...
Or you have to
like
think
an
about left and right
anti-commutator
or
kind of
something.
thing.
What's that?
Yeah, this ends up being like an anti-commutator kind of thing. Because what you have is you have like derivatives with respect to your ghost fields in there, and so those have like the left and right. I think they use left derivatives, but the point is, this isn't just trivial. And then so when you do that, but it's like the canonical transformation generated by the flow. This flow, right? This canonical transformation, right? And sort of flowing all your observables.
Okay.
In this way, and that's the BRST.
Yeah, that's my canonical transformation, right?
Right, and so.
So I have to, for any given whatever S is or does or something, I have to figure out a corresponding, like omega.
Right.
Yeah.
And omega is what like you sort of, when you go to quantum mechanics, a lot of what you work with is like omega, at least if you're thinking in terms of states, right? Because you just say that your physical states are in like the null space of omega.
Okay. So for like the Landau, or like when you do the Landau gauge, right? You have like the fake photons and stuff, and so you have to have the relevant part of it is in the null. Well, it's a little bit. I guess it's a null space or something. But it seems like it was a little more interesting.
Yeah. So, but I think we need to, before we get to that, I think we need to define a few more of the concepts from here. So, okay, so where were we before?
We're at the differential modulo delta.
Okay, I think we need to talk about differential modulo delta.
And then resolution.
And then resolution. And then I think maybe the elements of homological perturbation theory real quick. Okay. But I have to go at 3:30, so...
Do you want to skip to the resolution part?
Sure, I guess really quick. Okay, so the differential modulo delta is... Let's just do this real quick. I think this one should be easy to understand.
Yeah, basically it's basically using it to take homology of homology.
Yeah, Homology of homology. Wow. Okay, so we've got some differential, and d is an odd derivation. And we say that d is a differential modulo delta when we have d delta plus delta d, which this is the right commutator because d is an odd derivation, equals 0. So we have this, and we have that d squared is delta exact, which means d squared equals negative delta commutator for some,
There exists kind of thing.
yeah. Delta, right? There exists, if I wrote it this way, you could say there exists some delta such that, capital delta. Okay. So the first condition implies that d induces a derivation in H sub star, so the homology of delta. This derivation is still denoted by d. So the idea is we're modding out by delta or something?
So what we're doing, yeah, so what we're trying to do here with the
It's right in front of you is a big box of chalk,
oh,
right there,
okay.
so.
Wait, this is the one I was looking for. I feel bad using a new piece from this.
How those chalk trees were chopping down in the rainforest.
Can I erase this board?
Yeah.
So what we're trying to do here, let's see, so we're gonna take some,
Yeah, okay, one can consider the cohomology of d in H sub star of delta.
yeah, so
So that means you take
we have
H sub star delta, and then you mod by the kernel of d by the okay,
so what the goal of what we're trying to do here, basically our conditions on delta are going to make it so, or sorry, our conditions on d and delta are going to make it so that this is also going to be a chain complex. Because normally, so we take our homology of this,
yeah.
there's not like a nice way of immediately turning this into,
Right.
like, yeah, there's no way of just turning it into something like this unless we have these relations on, so we have what, that d delta plus delta d equals 0.
Okay, maybe we could talk about 8.27. So a cohomological class of d is thus determined by a delta closed element x. So I understand the delta closed element x that is d closed. Oh wait, no. Okay, so first, originally it's delta closed. Okay, element x that is d closed modulo delta y for some y. So dx equals delta y, and one must identify x with interesting. Okay. Let S be a differential, and let us assume that there's a grading of the algebra such that the expansion of S according to that grading starts with delta. Let D be the next term in that expansion. That is S equals delta plus D plus higher orders. Degree of D equals 1 plus degree of delta. Degree of higher orders is greater than the degree of D. Okay, this is, I think this is gonna be important to understand for BRST.
So when you have at the beginning of that sentence, you have an element, should we say an element Z or no?
Element
Y.
I think the idea is we wanna be able to
Y
combine
equals that.
two differentials in sort of a way, so, okay, so one of our differentials here is gonna be
Okay, I see where these rules come from. So, we're gonna take an element, S, in this homology. We know this homology is defined,
cohomology.
or
right?
sorry, thank you. This cohomology is going to be the kernel of D mod the image of D,
Mhm.
which tells us that we can essentially, we take a representative in the kernel of D. And that's going to determine, yeah, so yeah, we're basically, we just wanna pick something in each equivalence class. So let's just pick something in the kernel of D, which if it's in the kernel of D, it's going to be in one of the, it's gonna be in like this space, for example.
Mhm.
If it's in this space, this is going to be kernel of delta mod image of delta. So we take a representative X, so that delta X equals 0, because that defines an equivalence class in here.
Mhm.
That works to define our equivalence class in here. Or so that's, yeah. And then we also want that its differential is 0. So dz equals 0, which we can essentially think about our equivalence classes on. Yeah, so we can think about, so dz equals dx, and then because the way, or what we demand that D satisfies, the way this differential is defined is we pass it inside of the equivalence class.
Mhm.
We want this to be 0, but if this is equal to 0, then that means dx is equivalent to 0 modulo the image of delta,
Right,
which means that we can express it as delta y.
yeah. No, that makes sense. Yeah, I think, but I think,
Where was the previous Y before the delta Y?
I changed it to an S, because we had to use y later. Basically, we start with an element here, we pass it through some representatives, and then we end up getting that these two relations must
So-
hold on.
okay, so if you guys bear with me for a
For
sec,
some-
I think I can make the connection.
For some y thing?
Yeah.
For some delta y or something?
Y.
A y in where?
Can I erase this?
For some y in where?
Sorry, let me think. Some y in a sub n, I think. Might be plus or minus one. Something in this sequence here.
Oh, it has to be something that delta would
Yeah, basically.
have a tendency to wanna act on, okay,
Well, yeah.
okay.
It's yeah, you're basically just passing between like two different levels of equivalence classes, which is pretty annoying, but.
But okay, but here's the it's this I erased it. It's the idea that okay. So we're gonna when we do this, right? Remember we've got this D operator that's in BRST, right? This is in BRST. This is our longitudinal exterior derivative, right? So
Okay.
this is, and then they have this operator delta, which is a degree minus one thing, and that brings you from your whole phase space to the constraint surface. So it's like more like a boundary operator, right? It makes you go down in dimension.
So
right?
when you say D is a, longitudinal, what was the other verbiage?
Exterior
Derivative,
derivative.
okay, so before we had these things that we called like delta epsilon, and we said it acted on a F through Poisson bracket of epsilon, which is like an arbitrary function with F. Nothing to do with that?
No, it has to do with that. So the idea is that those delta
Remember there was
epsilon,
like a delta epsilon acting on F is the kind of,
delta epsilon acting on F
was
is
Poisson epsilon with F?
epsilon A F G A. But you can also think of this as the flows along. So I have to think about
These
where the
epsilons are
epsilon comes
gauge,
in.
they're,
But it's it's the flows of. So these gauge transformations are the flows.
these are different epsilons, right? Or,
Along
no, that's the same.
X, which X is the vector field that we get. Right, he did it this way. So this is our symplectic form, it's,
Yeah,
so,
which is something that I actually appreciate in a certain way.
yeah, so these are the vector fields that generate this. And then, but then the point is, we can, wait, what's the point? The point is this longitudinal exterior derivative is something that acts on the exterior algebra of these vector fields, right? And it does so in such a way.
What, okay, why do we want exterior algebras of vector fields?
Because, okay, the point is, okay, so what are our gauge invariant functions, right? Our gauge invariant functions should satisfy delta epsilon of F equals 0, right? Or,
I mean, they're okay, so they're defined to be, I thought, just something with an epsilon. But yeah, but they're what turn that weird integrand back into itself.
right,
You know,
right,
that
but
has
I'm
the
just saying,
PQ
okay,
dot
let me
minus
show you
H, right? The PQ
So
dot
I'm
minus
gonna have
H
to go.
minus multipliers times
right,
constraints. It's whatever turns that back into itself.
But, yes, but, okay, where is it? It's chapter 5, that's right. Computational longitudinal phase space. Okay, where? Yeah, okay, right. So they're ones whose where this equals 0, which means that the longitudinal derivative, so the derivative along these vector flows, equals 0, right? So he writes this.
So are we defining f there? F is one of those nice functions, or?
So let f be it's the 0 form. It's a 0 form. So it's a function on our constraint surface. So
it's defined on the constraint surface.
yeah, so now we're just talking about on the constraint surface, and that's important. So this delta is going to take you from functions on your entire space to functions on your constraint surface.
Okay.
Because it has to do with, there's two sort of things where you mod out. One is you sort of mod out your functions over the entire phase space by functions that vanish on the constraint surface, right? And then the other thing is that you mod out along the gauge orbits on the constraint surface.
You mod out by what there?
You mod out by the gauge orbits on the constraint surface. But to tell you the functions that are well defined when you do that, you look at this. So we look at the first. So the first exterior derivative is defined for functions by df of x. So this is a longitudinal vector field. So it's a
G.
which equals, whatever one.
It's whatever
directional derivative. Right?
Yeah, it's like a directional derivative that tells you the gauge
Right.
orbit direction.
So this is
Flow.
exactly the space of gauge invariant functions. But
Okay, so this is defining the
corresponds-
f's. These are defining the
This is H0 of D on our, maybe I'll put, on our constraint surface.
Oh, okay.
But now we kind of want to.
So H0 are some functions.
Yeah, H0 is functions, is the equivalence
Class of functions.
of functions that satisfy this or something like
Yeah,
that. Yeah. But it's functions that satisfy this. It's isomorphic spacing.
Okay.
Yeah. Yeah, that's right. It's functions that satisfy.
Okay.
So this is our H0 with this longitudinal derivative. But then we kind of, we want to sort of extend our space to cover functions on the whole phase space. But then we are only interested in functions, all of the functions. So if P is our phase space, we're interested in C infinity of P mod out by, he calls it script n, so functions that vanish on your constraint surface, right? And, okay, so I haven't quite figured out the map into here, but the idea is this is going to be a mapping that takes you from your phase space to your constraint surface. And the idea is what we're constructing with BRST is we're constructing some ass, which is which ends up being an odd differential here, which satisfies using this idea, H naught of S equals H naught of D, not mod, but whatever the modulo, D modulo delta, or whatever, the thing we've been talking about. Yeah, that thing.
So, okay.
And then this is a specific property of the BRST theory, though, because like in general doing this, but the idea is what he says is that this means that we create some operator. This is our BRST operator, and it ends up being delta plus D plus, this is what he writes, higher orders.
You mean smaller things? Or what do you mean by higher order?
I'm not, I think so. So like some
So these are all epsilons, but and then quotes as epsilon squareds and stuff?
Yeah, I think so. I think so. But the point is this, for us to be able to find the cohomology class the right way, this needs to be nilpotent. And so,
Oh, so
this
X-
won't necessarily be nilpotent, but you need to
Oh.
make, these are some corrections that make sure it's nilpotent. But it's
Oh.
like we're just trying to
So the corrections maybe
Yeah.
aren't really smaller or something?
I'm not sure. I'm not sure.
Okay.
But the idea is we're doing this, and then we end up getting that they generate the same. So it's sort of like, here's what I think is going on. Okay, we're creating some derivation on the exterior algebra. Whatever the right algebra is, the algebra of functions and like derivatives of functions and stuff on our phase space, on our entire phase space, that generates the same cohomology as the as this longitudinal exterior derivative does on our constraint surface. So it's like we're going back to the big phase space picture, but we're keeping the but we're trying to keep the same observables, basically.
Okay.
So
I
that's.
mean, which part of this seems like it's patently BRST guys discover it as opposed to, I mean, is this
Well,
is
it's,
it,
it's
this
a new
is it.
symmetry. Well, because you have to add ghost fields to make this work, and so it's.
Because, you know, Fadiv Popov, right, had ghost fields and stuff, but yeah, they didn't, I mean, I don't, you know, just notation, I don't see any S's and stuff, but I don't, but they, you know, had they were like, they, you know what their ultimate purpose was? It was ultimately in the whole, you know, path integral thing.
Right.
It was to keep you from overcounting gauge stuff.
Right. Yeah. It
And
was
getting
what was a determinant, right? Like it was a Jacobian.
Yeah, and there's like this real subtle thing he talks about here, that if you don't do the omega and omega star just right, you end up getting the inverse of the you know, you get 1 over the determinant. So you have to.
Well, that's why you need Grassmann numbers, because you would get 1 over the determinant if you did an integral over C number fields. Or it'd be
Well, he was talking about that you can even do kind of the right thing, but just the wrong order or something, and you get the.
Oh, maybe that's probably true. Anyways, I have to
Okay.
head out, but I'm also going to be out of town for most of this week. I'm probably back Friday.